Dave Stoblen here, working on sequences. Let's do an example problem and derive both recursive and explicit equations for a sequence. Let's say that we are going to make squares on our paper out of toothpicks. And so we're going to have a term number, and we're going to have a term, and term number 1 is going to represent one square made out of toothpicks, and the term value will be the number of toothpicks required. So for example, it might take 1, 2, 3, 4 toothpicks to make one square. To make 2 squares, it would take 1, 2, 3, 4, 5, 6, 7 toothpicks. To make 3 squares, it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. To make 4 squares, it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Are you seeing the pattern? What I'm noticing is that we start with the value 4, and our rule is plus 3 for each term. So using this information, it's very easy for us to write the recursive equation. You always need to know the value of the first term, which is 4, and then the value of any term n is equal to the previous term, which would be n minus 1, and then the rule. And so that's the recursive term. So this is how it would work. The value of a1 equals 4. The value of a2 equals a1 plus 3. And we know that a1 is 4, so that's 7. The value of a3, if that's n minus 1 would be a2, or the previous term, plus the rule. We know that that's 7 plus 3 is 10. And it continues to go so on and so forth. So again, if we wanted to know the 20th term, we would have to know all of the previous 19 terms in order to get the 20th. And that could potentially be a lot of work. So it would be nice then if we were able to derive an explicit formula that we could plug in the term number and get the value without having to know all the previous terms. So let's do this by making a table. We'll start with the n numbers. We know 1, 2, 3, 4, and 5. And then we know the values of the term for each term number is 4, 7, 10, 13, 16. And we have to see if we can get a pattern. Well, let's start. We know that a1 equals 4. We know that a2 is equal to 4 plus 3, which is 7. We know that a3 is equal to the previous term, 7 plus 3 is 10, but 7 is 4 plus 3, and then we just add another 3. And then to get the 4th term, we start with a 4, and now we add 3 3's. And to get the 5th term, we start with a 4, and we add 4 3's, and so on and so forth. So let's see if we can use this information to write an explicit formula. And so what I see is that for any term, we always start with the number 4, and then we're adding some 3's. And the question is, how many 3's are we adding? Well, here we're adding 1 3, and we need to compare that to the n number. Here we're adding 2 3's, and how does that compare to the n number? Here we're adding 3 3's, how does that compare? Or 4 3's, how does that compare? Well, if the n number is 5, we add 4 3's, which is really 1 less. So if this is n, the number of 3's is n minus 1. And that is our explicit formula. And this is really quite nice because if we want to know the 20th term, we don't have to know the previous 19. We can just plug in 20 and get the value. Now, let's do one other thing. If we were to graph this sequence and we put n on the x-axis and we put a sub n on the y-axis, well, when n is 1, an would be 4, and for 2 it would go up by 3, and for 3 it would go up 3 more, and for 4 it would go up 3 more. It looks like it would go up in a straight line, or be linear. Well, if we were to rearrange this function, if we were to rewrite it as an equals 3, n minus 1 plus 4, this looks very similar to y equals mx plus b, where that's the slope, that's the variable, and that's the y-intercept. And so, indeed, this happens to be a linear function in terms of a sequence.